Now it is my great pleasure to introduce Demetrios Pagonis. He is our ECOM seminar speaker today. Demetrios did his grad work at CU Boulder, working with Paul Simon. His work was about chemistry of hydroperoxides in SOA, indoor air quality, and gas wall partitioning in chambers, inlet tubing, and indoors. Demetrios is still at CU, and he is currently doing a postdoc with Jose Luis Jimenez. He's working with this instrument, the EESI, during FIREX-AQ, and today he will be talking about this project. With that, thank you, Demetrios, and you can take over.
Thanks, Ivan. Hello, everyone. Happy to be with you here today, virtually. In my talk today, I'll start off just by giving an overview of some frameworks of biomass burning aging. I'll introduce the EasyTOF instrument that I led the deployment of during FIREX-AQ, and then give overviews of the biomass burning OA emissions and the evolution of primary and secondary organic aerosol at FIREX. All right, so I won't spend much time today talking about the impacts that wildfire smoke can have. I have satellite imagery recently from the West Coast just showing just how big of an emission source fires are, just how widespread the impacts can be. This photo is from 2 p.m. in the Bay Area, right? And so the impacts on the radiative balance of the Earth and just total carbon emissions of fires are very significant. And for the western half of the country, these wildfire smoke events are the thing that are holding back improvements in air quality from the PM perspective. In the eastern half of the country, fires are also playing a significant role, but with a different paradigm here. So instead of these massive fire events, you have many, many small fires. So these can be just single fields that are being burned or land clearing burns. And this is one of the culprits for degraded air quality in the southeast US as well. So when we think about the OA budget in the context of smoke, sort of the key questions we have are just how much biomass burning OA being emitted. As it ages, is that aging producing more OA as it travels, or is it being consumed and being removed from the atmosphere by chemistry? And as it travels, which chemical processes are the ones that are most important, right? Can we make measurements in the field that can help guide lab studies into productive areas? Right. And so I'll show here, this is a pie chart of the fractional composition of PM1 at a representative fire during FIREX. Right, what we see is that organic aerosol is what dominates the mass, and that's what I'll be talking about throughout this seminar. There are other members of the FIREX science team that we're collaborating with, looking at the evolution of the inorganic fraction of PM1, but I won't be touching on that today. Okay, and so as we talk about smoke aging, I'll refer a lot to these normalized excess mixing ratios of either total organic aerosol or components of OA divided by the excess mixing ratio of carbon monoxide. And if the way this gets presented often is you normalize that value to the value you get closest to the fire, so you just start it from a reference value of 1. Right, and then if you go through the literature, so Anna Hodgscher has a nice review that compiles many field and lab measurements of the aging of smoke OA. There are times where you see net increase in OA relative to CO, but most often you get a net decrease. And so in terms of the physical processes that could either drive you to get production or loss of OA, one of the key players, the way we think about smoke aging is secondary organic aerosol production. Right? So along with primary OA emissions, you also get substantial VOC emissions from fires. And as these VOCs are oxidized either by OH or ozone or NO3 radical, they can produce lower volatility gases that then partition to the aerosol phase and increase the aerosol mass. On the other side here, we've got OA evaporation. If you go in and you write out your equilibrium expression for gas particle partitioning, key terms are going to be the volatility of a compound and the total amount of OA. And so as you rearrange terms there, you can write an expression for the fraction of a given compound that's in the particle phase, right? So that's the mass in the particle divided by the sum mass of what's in the particle phase and the gas phase. Right? And what that depends on is the total concentration of OA, COA, and the volatility of the given compound expressed as a saturation mass concentration, C star. And what this means is that just through dilution alone, as you decrease the mass concentration of OA, you will drive evaporation of components of aerosol even without any additional chemistry. Right? So dilution alone is enough to drive evaporative losses. And so if there were no chemistry happening, we would always expect there to be a gradual decrease in the ratio of excess OA to CO. And of course, these two processes are not uncoupled. You can have oxidation of these gas phase compounds to form lower volatility, which would both deplete the gas phase, driving additional evaporation, while also producing new secondary organic aerosol. And so I'll circle back to that quite a bit later in the talk. So this framework has been around for quite some time, this idea that you have SOA formation balancing primary OA loss in smoke. You can trace it back at least 20 years in the literature. And there have been, in addition to all the field studies, this has been studied extensively in the lab. And so here we're looking at, this is an OA enhancement ratio. That's the same value I was showing on the previous slide. And I just want to focus here, this is from the Hodge review paper, just on the comparison of all lab campaigns to all field campaigns that are included here. So the lab campaigns have been very efficient in generating SOA and looking in very detailed ways at that chemistry. But in the fields, we're generally getting more loss. And so the lab work has really nicely characterized the SOA side, but it seems like there's more happening in the field, and the potential POA evaporation side has not been addressed as thoroughly. One other study I just want to summarize here is a paper by Mike Kubison for measurements made at ArcTest with an aerosol mass spectrometer. And here this is using two marker ions in the AMS spectrum that each represent one of these two processes. And so this F44 marker, which is the ion at a mass to charge ratio of 44, its fractional contribution to the total signal in the AMS, is representative of secondary chemistry. And you can see that the marker representative of secondary chemistry is increasing here as plumes age. Well, this other marker here, F60, is representative of levoglucosin and also other compounds. And its fractional composition is highest close to the source and decreases over time. I do want to call a bit of attention here to these values in non-biomass burning impacted AMS studies that are in this figure, right? Showing that while F60 is a good tracer for biomass burning influence, there's huge natural variability close to sources. And that's in part just because F60 is not specific to a single molecule. It's sometimes dominated by levoglucosin, but you can see that there's a lot of variability here that really makes it clear we need more targeted measurements of the POA in smoke. Right, and so just from a historical perspective, this framework's been around for a while, but what we've been missing is field measurements of both processes occurring on the molecular level. Right? And there's quite a few challenges that have been in the way of doing this. Generally, speciated OA measurements have been slow in the context of airborne studies. You're either collecting aerosol on filters or using a particle into liquid sampler, and that requires a bit of time. So you're not able to fully leverage the power of airborne sampling with these slower techniques. Second is that a lot of the components of POA are simply not volatile aloft. Right? The plumes are concentrated and quite cold, and so a lot of the semi-volatile markers that we know are just not evaporating out of POA when you try to measure them from aircraft. And lastly, fires are highly variable, and so getting good characterization of smoke aging is quite challenging in light of that. Right, the typical sampling approach of measuring smoke from the air is to go ahead and just fly patterns back and forth across the smoke and do this semi-Lagrangian sampling. Just because of practical constraints, right, we're generally measuring many hours of aging in a much shorter amount of flight time. Right, so it's smoke that was emitted now 6-7 hours apart. And in that time, fires evolve, they can strengthen and move into different fuels, change flame states, and that's going to change your emission profile and change your chemistry and really complicate your analysis as you try to compare chemical composition across these different transects. If you have fast measurements, though, you can leverage that into looking at gradients as you fly across the plume during each one of these transects. And so these are figures from Lauren Garofalo's paper last year with AMS data from the WECAN study, again looking at those same two markers that I was showing from the ARC-TAS study. And so what she's showing is that the marker for secondary chemistry is enriched in the wings of the plume and depleted here in the center. And similarly, the marker for the POA is enriched in the center of the plume, but then depleted out on the wings. Okay. So working our way back to the second challenge that I had listed in terms of which components are actually semi-volatile in biomass burning OA, right? So, right, which components end up being equally partitioned here between the gas and the particle phase. And so what we can do is we can take our expression for calculating the fraction of a component in the aerosol phase, set it equal to 0.5, and then take the temperature and the concentration of OA conditions that we experienced at FIREX and generate this histogram here of showing what the C star at 298 K is in each transect that is equally partitioned between the gas and particle phase. And what we see is that it's compounds that we would typically consider as being more on the volatile side, or what partition equally, right? So as you go to cooler temperatures aloft, you really suppress vapor pressure, right? And so something that is often considered a semi-volatile component of primary smoke OA, like levoglucosin, is actually almost entirely in the particle phase in these conditions. And so people have tried to do airborne measurements of levoglucosin in smoke plumes, but they've just been in a regime where all the levoglucosin's in the aerosol phase, and so it then becomes very hard to measure its evaporation as you go. All right, and then finally, to address the challenge of instrumentation, we've brought new advanced aerosol techniques to the NASA DC-8 for FIREX-AQ last summer. And so this was 21 research flights measuring both Western fires out of Boise and then smaller Eastern fires out of Salina, Kansas. And we had 2 mass spectrometers on board. First, over here on the right side of the rack, we had the high-resolution Aerodyne Aerosol Mass Spectrometer. This instrument's been in use in Boulder for a while, so I won't spend much time on it. I do have some of the standard data products here for you. And then here on the left-hand side is the extractive Electrospray time-of-flight mass spectrometer that we flew for the first time during FIREX. And so the EESI is its data product that we've been generating is targeted quantification of both Glucosin and Nitrocatechol in PM1. And so here we're doing targeted measurement of individual OA components in order to complement the bulk properties of OA that are being measured by the AMS. So EESI is not a widely used technique. It's been around for a little while and has recently gained traction as it's become more sensitive. And the way it works here is we sample the ambient air in to this region, which we keep very tightly pressure controlled in order to be able to do Electrospray. Electrospray is a very pressure sensitive ionization technique. And so we need to have very tight control on pressure inside of this as we move up and down in the atmosphere on the plane. Then everything passes through this multi-channel charcoal denuder, which is used to strip away gases while passing particles through. That's because we would otherwise detect the gases here with the Electrospray, and we just want to measure what's in the aerosol phase. Right, and so then the particles themselves here pass through this Electrospray, and there the analyte aerosol collides with the much larger Electrospray droplets, gets solvated, and then these particles they're highly charged, and they undergo your typical evaporation of Electrospray drops, followed by Coulomb explosion until you get ionization of your analytes, either as adducts with sodium, if you're operating with positive ion polarity, or you just get a deprotonated analyte when you're operating with negative ion polarity. And so we flew with both throughout FIREX, and I'll go ahead and show you some of that data here. So for positive ion polarity, our targeted analyte is Glucosin, which I'm showing you here. There are isomers of Glucosin, like manosan and galactosan, where you're changing the stereochemistry for these three hydroxyl groups, whether they're pointed up or down, the way it is drawn here. And those, of course, are all going to be detected together at the same formula. But Amy Solomon has made very nice pills with liquid chromatography measurements showing that in most smoke plumes, Glucosin is by far the dominant isomer. And so for simplicity here, I'm just going to call the collected anhydroglucoses Glucosin. And as you can see here on the right side, I have 1 Hertz data for Glucosin inside of a smoke plume with carbon monoxide overlaid to show you that all of this variability is in fact plume structure and not just noise in our data. In negative ion polarity, we're targeting Nitrocatechol. This is a product of secondary chemistry with the either OH radical or NO3 radical oxidation of catechol. And so there's been nice work by Zach Feinwax quantifying the yields of this in these reactions. And it's a very nice marker of secondary chemistry here. And so the real strength here of EESI is that it is fast. We're getting 1 Hertz measurements. The time response is quick, both on the rising and falling edge. Response is linear with concentration, and we have minimal matrix effects. And that's unusual for an Electrospray technique. But we're able to achieve that in part because of how dilute the aerosol is after it's consumed by the Electrospray droplet. Our detection limits are quite low, especially in negative ion polarity, between 10 and 20 nanograms per cubic meter. So this is standard cubic meters at 0 C and 1 atmosphere. And so you can see here that we're getting at 1 Hertz data here over 3 minutes. We're still getting fast response on the rising and falling edge, even all the way down at the detection limit of the instrument. And so this is a really powerful technique for speciating OA, and it's opened up a lot of new possibilities in terms of analysis we can do in terms of aerosol chemistry. I want to take a quick detour here to address a common concern with these chemical ionization techniques, which is just how many isomers and how many different compounds are contributing to signal at a single mass. And so all through FIREX-AQ, we collected filter samples, just here, standard 47mm filters. Here, Pedro is transferring a collected sample to its holder in order to be frozen and shipped off to Alex Laskin's group at Purdue. And there, Carlos Simons has been running liquid chromatography, electrospray ionization orbitrap mass spectrometry on all of these filter extracts. And what she's shown here, this is actually extracted ion chromatograms from actual smoke samples. So this is a field sample showing a single peak for each of the 2 ions that we're studying with the EESI, and the retention times here of these peaks match the standards we sent them perfectly. And so this is very strong evidence that what we're measuring is just signal from individual compounds. And so we're confident in calling these levoglucosin and nitrocatechol. In order to demonstrate that we are quantitative, we have a nice intercomparison here with 3-way intercomparison between a Sheridan instrument flown by Armin Wisthaller's group for one flight, the EESI, and the AMS that was flown by our group. So what I'm showing here first is, once again, EESI in blue and carbon monoxide in black. And in green, I'm showing what's called AMS equivalent levoglucosin. And so this is taking that marker at mass to charge 60, just here written out as the high resolution form of that marker, right, where we assume that all of this signal came from levoglucosin, and we calibrate that with the levoglucosin standards that we were running all through FIREX. And so this is a quantity that's been used in the literature before as a levoglucosin measurement, but it's been known for a long time to have a lot of contributions from other species. And so as we expect here, our slope is significantly greater than 1 because the AMS equivalent levoglucosin is not actually a specific measurement for levoglucosin. And for the Sheridan instrument, this is a proton transfer mass spectrometry technique where aerosol is enriched relative to the gas phase and then vaporized and ionized inside of a PTRMS. And when we overlay this here with the EESI, we get very good quantitative agreement. And so our regression slope on 1 Hertz data for this entire flight where the Sheridan was on board is 0.93. And quite a bit of this scatter that we have is just driven by the difference in time response between the 2 instruments. The Oslo PTRMS was on the DC-8 to measure ammonia. And so they were equipped with a gas phase inlet. And so when they installed the Sheridan for a flight, they had to run their inlet all the way across the plane and had a long residence time. So that's a contributing factor to the broadening here. But this agreement with the Sheridan and the EESI is by far the strongest evidence we have that the EESI is not susceptible to significant matrix effects in the electrospray ionization. Many groups, including us, have done tests with binary mixtures in labs showing that sensitivity stays linear as you mix in other components, but this is demonstrating it in actual OA, like a true complex mixture, and we get good quantification across these instruments, which we're very happy to see. All right. Okay, so moving ahead here, I'll talk some about the summary of the biomass burning OA emissions during FIREX. And so what I'm showing here, each point in these 2 plots is a single transect through a smoke plume. So every time we cross a smoke plume, we've added a point to this plot. So I'm showing the excess mixing ratio for OA against the excess mixing ratio for CO. And for the sake of reducing clutter, I've separated out wildland fires in red from the agricultural fires in blue. But I'm showing the regressions for both on both plots, just so you can see the difference in slope here. So as you can see, the agricultural fires have seem to have a lower emission ratio here than the wildland fires, and that seems to be robust across all of this sampling. Looking at levoglucosin on the EESI side, we see actually that we get the same slope across both wildland fires and agricultural fires, and so these emissions were fairly consistent all through the campaign. Meanwhile, for nitrocatechol, which is our marker of an indicator of secondary chemistry, we see significantly more nitrocatechol in our OA when we're sampling wildland fires than when we're sampling the agricultural fires. And one of the reasons for this is that we're sampling significantly older smoke, generally speaking, in the Boise leg of the campaign. And so there's been a lot more time for secondary chemistry to happen and to produce nitrocatechol from the gas phase catechol. On the next slide here, I'm just going to keep all of the data that I'm showing exactly the same, but everything's going to switch to a log scale. And you can see here that these relationships are holding up across the full range of concentrations that we sampled at FIREX. One thing I do want to note is that for the total OA values, we're sampling generally at significantly colder conditions and higher altitudes here for the wildland fires. And so temperature is certainly playing a role in the difference in the slopes that we see. And I'll talk more about that later on. Okay, if we go ahead and just produce campaign-wide summaries for these three values, I'm also showing the campaign summary of MCE that calculated by Hannah Halliday. Right, we see the same trends that I was describing in the previous slides, which is higher OA to CO ratio in the wildland fires, higher nitrocatechol ratio in the wildland fires, and similar results in the agricultural fires. And as has been seen before, lower MCE for wildland burns. Looking at our values here, our OA to CO values here. So now this is just the mass ratio of each is consistent with what was seen at WCAN, spanning similar ranges of MCE, and we have our additional parameters here from the EESI from FIREX. Okay. So moving on here, going to look into evaporation of primary OA and see what the EESI was able to measure through FIREX-AQ. Here, this is the same histogram I showed earlier of which volatilities are semi-volatile during each plume transect of FIRE-AQ. And just want to point out that levoglucosin here is all the way here in the left tail. And so for pretty much all of the conditions we sampled, levoglucosin was pretty non-volatile. But we did get lucky at one point, and there was one significant exception to this, and that was our flight to the Sheridan Fire on August 15th. And so this was a good day for the Western United States. This was the only fire that was a clear target for us to sample. Otherwise, it was good fire weather. And so when we got down to Arizona, where this fire was, we didn't even find a coherent plume. We found a pretty complicated injection above this fire where smoke from earlier in the day was lofted above, as you can see here in the LiDAR image. And then smoke that was emitted later had been partially lofted and was descending back down towards ground level. We've been working with Pablo Said and Laura Thapa at UCLA, working to understand the dynamics of this plume rise, because it is a pretty messy picture. But we are starting to see that this smoke was partly lofted and did do some descending. And one thing about this sampling, so you can see the flight track of the DC-8 here is this black line through the data. We were flying with visual flight rules because this was a pretty optically thin plume. After arriving at the fire and seeing the structure, mission scientists just took a tablet to the pilots, showed them this plume, and asked them to just fly a descent straight through it. And so the pilots simply watched the real-time LiDAR imagery coming in and adjusted their descent rate to match, and really did an incredible bit of flying here to take us down through this plume. And the value in this is that as we descend here a couple kilometers, we get about a 15K increase in temperature. And so this is a chance to just do a really nice natural experiment on thermal denuding of OA at different altitudes. And so what I have plotted here is we have the ambient air temperature here on the y-axis, OA concentration on the x. Then I've overlaid contours of the fraction in the particle phase for levoglucosin. And so at the top of this run, over 95% of levoglucosin is calculated to be in the aerosol phase. Then as you descend, lose about 40% to evaporation, or at least that's what the theory predicts. So go ahead and pull up our data here, and we do in fact see measurable decrease in the normalized excess mixing ratio of levoglucosin as the plume is heated as it descends. And so we lose about 34% of our levoglucosin. This is data averaged now to 1 minute as we make this descent. And about 34% of our levoglucosin evaporates out. And we also see measurable OA loss. So we're not just denuding the levoglucosin, we're denuding organic aerosol. And non-volatile components like black carbon here, we're seeing no decreasing trend. Right, so the non-volatile components are staying in the particle phase, and the semi-volatile components are evaporating out. Now, in terms of whether or not the extent of evaporation looks good, this lines up very nicely with ground-based thermal denuder measurements that Alex Huffman made some time ago. And we also, sorry, I think someone just got home from daycare. Yeah, and so this gives us good confidence that we can set out and do more detailed modeling of this partitioning. And so first up is just a simple single component model of gas particle partitioning, looking at levoglucosin. So here, just looking at the normalized excess mixing ratio of levoglucosin across temperature. And what we do is we constrain the OA concentration to our measurements, and then we vary temperature and dilute based on the measured carbon monoxide mixing ratio and the ambient temperature. And when we do this dashed line here, this is our model for a compound with a C star of 6 micrograms per cubic meter. And now the measured value for levoglucosin in the literature is 13 micrograms per cubic meter. And if you use the structure-activity relationships that are out there to estimate the vapor pressure, you get a similar value to what's measured. And so this is a factor of 2 off, but if you've worked with measuring or estimating vapor pressures, you likely appreciate that that's very good agreement here, since this is a model of idealized gas particle partitioning. Right, that's neglecting things like activity coefficients. Right, and so we're really quite happy with the agreement we're getting here. Right, and so since this works very nicely for a single component, we've also set out to model bulk OA concentrations. And the way that we're doing that is using a volatility basis set, or a VBS. Right? And so where before we were simply modeling the partitioning of a single component, we've now taken all of the non-volatile and semi-volatile organic compounds and lumped them into, in this case, 6 distinct bins, separated by an order of magnitude in volatility space. So the VBS we're using is a published biomass burning OA VBS from Andy May. And what we do is we simply initialize the VBS to the conditions at the top of the plume. That's what I'm showing here in the figure on the left. So we're at 285 K and 66 micrograms per cubic meter of OA. And then just like in the previous model, we're going to go ahead and dilute this parcel and change its temperature the same way that the smoke we sampled in FIREX was treated. And so here what I'm showing is now at the bottom of the run where things have been both heated and diluted slightly, right? And you can see that this volatility basis set is predicting that we should drop down to about 38 micrograms per cubic meter of total OA, right? And so here, both the dilution and the shift in volatility caused by the change in temperature are driving OA evaporation. Right? And if we calculate these VBSs for each data point in this 1 minute data, you can see that we're also getting really nice agreement. Right? And so just using literature values for volatilities and literature volatility basis sets, we're reproducing this, the thermal denuding in this natural experiment very well. And so we feel like we have a really nice handle on what the POA is doing in this plume. All right. So moving on now, we're going to talk a bit about the SOA production. Right? So we saw nice evidence for POA evaporation, and now we'll go look at the other side of the coin here. All right, and to do this, I'm going to use a single fire, the Williams Flats fire, as a case study here. We went to this fire on several different days, and we flew semi-Lagrangian patterns 5 times across 3 research flights. So the 3rd of August, the 6th, and the 7th. And so starting here on the left side with the OA data, if we normalize all the different Lagrangians to their initial value here, I just want to point out that across 3 days at the same fire, we actually spanned almost the full range of variability that's in the literature. Right? And so while fuels and flame state did change as this fire grew, it is all ultimately the same fire. And so if we had only measured it once, we could have wound up at any point in this range that's in the literature. And so it's just an impressive testament to the amount of variability in what these fires can put out and how those emissions evolve. In the EESI data for levoglucosin, we see consistent levoglucosin loss in each of these transects. I'll circle back to that soon. And lastly, in our marker of secondary chemistry, we see pretty mixed behavior. So for the 3rd and the 6th, we're not seeing clear evidence of nitrocatechol production. We're actually seeing it looks like nitrocatechol loss. And then for the 2 transects on the 7th, we can see some very clear trends in nitrocatechol production as we go downwind. In fact, for this first transect, if it weren't for the last point where there was hardly any nitrocatechol at all, we would have our highest production rates there. Okay, and so this brings me to my favorite figure from the campaign. This is time series from one of these semi-Lagrangian patterns as we worked our way back and forth across the fire, successfully sampling further and further downwind. You can see that the nitrocatechol concentrations measured by EESI just grow in steadily relative to CO in each transect, right? So this looks exactly like how you would have sketched it out ahead of the campaign and what an ideal marker of secondary chemistry would look like as a plume aged. And so not only do we get significant variability as we travel down the plume, you can see that we also have very strong cross-plume gradients in a handful of places. And we can make use of that here, since these gradients appear in essentially all of the measurements in this plume. So it appears in a lot of the gas phase compounds, in ozone, and various components of NOx. And it also appears in the positive matrix factorization of the AMS data. And so this was completely unconstrained TMF of the AMS spectra. It does not use the EESI measurements as input in any way. And you can see that this factor that we're calling the Nitrocatechol SOA factor is giving us this exact same cross-plume gradient here. And so it's following our representative SOA compound very well. And so we're calling this a secondary organic aerosol factor. And as you can see, comparing the mass concentrations of each, there are many more components than just nitrocatechol in this factor, right? And so this is representative of a lot of SOA production happening inside the plume. So if we go ahead and we take all the various factors in the AMS spectrum, and we run through the type of reasoning that I was just showing you on the last slide in terms of downwind evolution and cross-plume evolution, we can sort them each as primary or secondary OA. And when we do that, we can see that the SOA fraction of the total OA doubles over the course of about 3 hours of aging. Right, and in that time, we're getting over 100 micrograms per cubic meter of OA production per hour. So very impressive turnover inside of this plume. And then similarly, each of the factors that we've called POA is being lost as we travel. And so the net effect here is that our mixing ratio for OA is sitting flat despite all this change in composition. Now we'd like to say that this completes the story, but there is a bit more complexity here on the POA side that we're very much still working on understanding. And so here I'm bringing back the evolution of levoglucosin in each of these plumes for the 3 flights where we were sampling with positive ion polarity. And so if we go ahead and we take these loss rates, each of these plumes is very concentrated and around 0C. And so at those conditions, there's very little levoglucosin in the gas phase. And so if we just set up a simple box model and try to reproduce these loss rates, we have to turn up OH to about 10 to the 8th molecules per centimeter cubed to reproduce these loss rates. And that's just not a realistic concentration. Right, and so there's certainly some heterogeneous oxidation going on inside of these plumes. That's consuming levoglucosin in the particle phase. So whether that's heterogeneous OH oxidations or other condensed phase reactions, that remains to be seen. But Mindy Schoenemann in our group is working on chamber experiments and further analyzing FIREX data, just trying to tease out how much of this conversion is happening inside particles versus in the gas phase. All right, so the last topic here is just trying to combine what we've seen in terms of bulk OA properties and looking at these properties across the entire campaign to try to see just how well we can use other parameters to predict the evolution of OA concentration downwind. And so, we were looking at this figure and looking at just how much more OA there was when we were sampling wildland fires than agricultural fires, and looking at the significant temperature difference between the two here, right? And so on average, a transect through a wildland fire smoke plume was 25 K colder than a transect through an agricultural plume. And so that has a significant effect on volatility of components in the plume. And so, we're curious just how much of this extra OA is just explainable due to the decrease in temperature. And so we know that there's of course variability in emissions across fuel types and flame state and contributions from aging. But this is just looking to set out and see, how well can we do if we ignore all of that and just use a single volatility basis set to try to explain an entire campaign of data. All right, and so to do this, we're just going to take the same VBS I showed you earlier, set an emission ratio to CO, and then just partition it at the temperature and pressure that we sampled, right? So is a CO measurement alone enough to constrain, to predict the OA concentration? Now, before I show you the VBS approach, we need something to compare it to. And so what I'm comparing this to is just a very simple emission ratio parameterization where we just set a single emission ratio of OA to CO for the entire campaign. And so we go ahead and we use a scale invariant two-sided regression to get that emission ratio. And then from that, we can simply predict OA from the excess CO. And that's what I'm showing you here with points colored by temperature. And things are generally, the predicted OA is generally agreeing with the measured OA in this plot within about a factor of 2. But if you go ahead and really look at the residuals, you can see that there's a couple different biases showing up here. First is that this approach is under-predicting OA at low temperatures. So these are the darker points here. And then as you move to both lower OA concentrations and higher temperatures, this approach then begins to overestimate the OA concentration. And that's exactly what you'd expect for a parameterization that's ignoring the role of evaporation and gas particle partitioning. So now I'll go ahead and compare this to a VBS approach. These are the same steps I outlined before. So once again, we're setting a single emission ratio, but instead of setting it for all OA, we're setting it for an entire volatility basis set. And then we partition the VBS at the corresponding temperature and pressure. And I should, of course, note this is exactly the approach that Andy May recommended in his paper as a way to try to improve estimates of OA concentration. So when we go ahead and do this, I'll point out a couple of things. First is that we've tightened up the agreement here and brought a lot more of our transects here within a factor of 2. And second, we've eliminated both the temperature and the OA concentration bias that we were seeing when you use a single emission ratio for OA directly. And so we think this holds a lot of promise for helping predict OA concentrations downwind of fires. This is all just being calculated directly from a measured the measured carbon monoxide, and so it's still not feasible to include a full chemical treatment of OA in every model, but we think something like this is much more can be implemented much more readily and holds a lot of promise. And so let's see. So going forward, I should mention, of course, that we have airborne and thermal denuder measurements during FIREX that we're going to start analyzing, and we think that we can use those to further refine the VBS that we use in this approach, and then maybe by also incorporating some speciation in fuels, we could start to do even better than a factor of 2. And then lastly, if you just want to see those scaled residuals as histograms, you can see that the VBS approach in red is a much better looking distribution than the single emission ratio approach. All right, so just to wrap up here with some conclusions, we've gotten direct molecular evidence for both POA loss and SOA formation through the EESI data at FIREX-AQ. And so we've constrained POA evaporation, both on the molecular level and for bulk OA. We've set out quantifying the SOA production rates in these plumes and the POA loss rates. And then we can use this to really start to improve predictions of OA concentrations downwind of fires. And with that, I'd like to thank Yvonne and ACOM again for inviting me here, and thank you all for listening, and I'm happy to answer the questions that you have.
Thanks, Demetrios. That was very interesting. Now it's time for questions. I guess we can start with questions. If you have questions, please submit your questions with in the Slido link. I think I can probably start. This is a very basic question, Demetrios. So for the weighted excess mixing ratios, can you explain again? So how do you define the background, and if the background of, for example, CO changes during the flight?
Yeah, so for all of these, we've gone through and just defined reference background periods outside of the plume for each transect. And so generally speaking, the plumes were clearly defined enough that we do have a nice clear background that we then see enhancement of and then come back down. So in terms of the details of how we set that, we use the formaldehyde, black carbon, and carbon monoxide measurements all simultaneously to identify a consistent background across the three to say when we are clearly outside of the plume versus clearly in it. Yeah, and then we just subtract that background off of the plume values. For a lot of the Western fires, that subtraction makes almost no difference because the plumes were so thick.
Okay, that makes sense. There is a question from Ali, PhD student at CSU working with Jatar. You mentioned that wildland fires are relatively aged in compared with agricultural fires. Have you thought about SOA POA splits by the first transect of wildland fires? And can you see May et al. Volatility for the first transect since he reported POA volatility? You can probably see the question.
Yeah, so for the first half of that, for the SOA POA splits, what we're seeing on the AMS side and from the Nitrocatechol data is plenty of SOA at the first transect. And so that there's definitely been aging by the time we're able to get to it, right? We aren't flying directly in the smoke column. And so I think for the plot I was showing, the aging started at almost an hour. And so there's certainly an SOA contribution. And in terms of how representative the May VBS is, when we have so much SOA, yeah, we're hoping to explore how much that factor of 2 spread we have is, whether that's differences in the emissions themselves, or if that's evolution of the consistent set of emissions as it ages. But right, so just in that exercise of ignoring aging and ignoring fuels, that VBS got us within a factor of 2. And so it may be that the changes in chemical composition with different emissions or different aging don't actually change your volatility distribution that dramatically.
I have one additional comment. Are you aware of, I mean, everyone right now is grounded, I guess, because of pandemic, but right now there are many fires, active fires. Are you aware of any studies of wildfire chemistry right now? Probably not.
Sure. I know locally, a lot of people here in Boulder have had instruments up and running since the spring doing ambient monitoring. Just from comments I've heard at other seminars, that what started as investigating air quality during quarantines and stay-at-home orders sort of segued naturally into the smoke impacts here on the Front Range. I certainly haven't heard of any ongoing field efforts, but it may be happening, and I just don't know about it.
Okay, I don't see any more questions. I think everything was clear. Well, with that, I would like to thank you, Demetrios, and thanks everyone for joining. And I will keep you posted with future seminars. And yeah, thanks, Demetrios. I appreciate it.
Thank you all.
Bye-bye.